Hi all, welcome to another video of compressible fluid flow video lecture series. We have derived a rate equation for conservation of mass, momentum and energy in the past 3 or 4 videos, and we have one more rate equation left to be derived, which is entropy equation. So we will be deriving entropy equation, rate equation for entropy in this video. So let us look into that. Entropy change in any steady irreversible process. This is as per the second law of thermodynamics. We all know that as per the second law of thermodynamics, the entropy, heat transfer and temperature will be connected by this expression, which is dq by t, which is less than ds. Now we are changing this equation in order to find our rate equation. Therefore, dividing the left hand side and right hand side with a dt, the expression will be changed like this. Now we will consider the unsteady flow. Unsteady flow is nothing but without assuming the steady flow. In the previous equation, previous derivations, we have assumed the case of steady flow only at the end of the derivation. So it was unsteady flow throughout when we have started all those derivations. So here also, first we will consider the unsteady flow through the control volume. We will consider the control volume approach. So here the rate of change of entropy, which is ds by dt, which is the right hand side of this expression, that will be equal to the rate of change of entropy within the control volume plus the excess of the outgoing entropy flux over the incoming entropy flux. This is nothing but nothing but what we have done in momentum and energy equation derivation. We have done the same consideration in that cases also. So let us see what is this. This means 1 by t dq by dt, which is left hand side, which is less than this whole ds by dt will be converted into 3 terms. And the first term will be the rate of change of entropy within the control volume. Okay. Therefore, we can write this S, capital S can be written like this, integral control of volume ds. Okay. So this whole term will be denoting the control volume. So dou by dou t of integral Cv ds. This is the first term, which is the rate of change of entropy within the control volume, plus the excess of outgoing entropy flux. Entropy flux is denoted by S dot, and the excess of the outgoing entropy flux over the incoming entropy flux is denoted by this two terms: integral outward ds dot minus integral inward ds dot. Okay. Now we have brought density term into this equation. To bring the density, we have changed the right hand side components like this. Let us take the first component, which is dou by dou t integral Cv rho, which is density, small s, which is specific entropy, and dV into dV. Now looking into the unit of this term, rho is mass by volume, and specific entropy is capital S by mass. So masses will get cancelled and a volume will be remaining in the denominator, and the unit of this volume and the denominator volume will get cancelled. So our unit will be capital S by a dou t will be therefore that will be our entropy flux, entropy per time. Okay, so the unit is conserved. Now taking this component rho SCdA, rho is density, which is mass by volume, and small s is specific entropy, which is capital S by m. Masses get cancelled, a volume remains, and C into dA is actually dV, which is arbitrary change in volume. Okay, so C into dA, which will be dV by time, dV by time, arbitrary change in volume per time. So a volume is remaining here, and that volume and this volume will be cancelled, and time will be remaining in the denominator. So here also we have entropy by time. So here also the unit of the term is conserved. Same will be coming here in the inward flow. Okay, so by this process we have brought the density term into our equation, so that we can simplify this equation further, and that simplified expression can be for the use for considerations and also for the problem solving. Now this can be considered as the integral form of the entropy equation by using the control volume analysis. Now in vector notation, we all know what is the vector notation. We can write this outflow and inflow terms as a single term, which is integral Cs rho S C dA. And for the steady flow consideration is dou rho by dou t is equal to 0. So here this term dou rho by dou t will be equal to 0. So this whole control volume term will be equated to 0. Therefore, equation will be simplified like this. Only the vector notation, which is surface integral term, will be remaining on the right hand side. For steady one-dimensional flow, here we will be integrating this dA. We will integrate this dA, and we have rho into C into A, which is nothing but mass flow rate. Okay, rho AV. We all know that rho AV is mass flow rate from our previous subjects, but here instead of V, we will be denoting C for fluid velocity. So this rho AC will be mass flow rate, and we can take the mass flow rate outside, because as per the law of conservation of mass flow rate will be constant. That's why we have taken the m dot outside. So inside the integral, only the entropy term will be remaining. So after integrating the entropy and applying limits, in brackets we can write S2 minus S1, which is the entropy for the outflow minus the entropy for the inflow. Now the final consideration will be for adiabatic flow. For the case of adiabatic flow, we all know that change in heat transfer with respect to time will be equal to 0. Therefore, dq by dt equal to 0. This whole left hand side will be equated to 0. That means S2 is greater than S1. This is as per our second law of thermodynamics. Okay. So this can be a presentable manner which can be derived from our integral form of the entropy equation based on control volume approach. Okay. So we have now derived all the right equations. Now our right equations considered were conservation of mass, conservation of momentum, energy, and entropy. Now, before going to the numerical part of this topic or module, we have to consider some more concept. And one important concept to be understood is wave theory. So wave theory, we all know that we all know what is wave theory. We have studied that in our physics, in our plus 2 physics. But we will be concentrating more, or we will be studying a little deeply on this subject about wave theory. So before going to that topic, we have to understand what is bulk modulus of elasticity. This is also a recurring term. We have studied about this term in our mechanics of solids subject in our previous semester. Let us see what is this bulk modulus of elasticity.